Hi everyone. The problems on this playlist are essentially meant to challenge your understanding of the second fundamental theorem of calculus and allow you to apply it to a series of problems that have some relationship to derivatives, which is why the second fundamental theorem plays in. As a reminder, the second fundamental theorem is about taking the derivative of an integral. So the common theme that ties together all of the questions on page 10 is that they're derivative problems that in theory should trigger some of our memories from first semester when we were focusing on derivatives all the time. I'll make the disclaimer that on page 10, these questions are a little bit more challenging than what you saw on page 9. The goal with these questions is to take the fundamental theorem and apply it in new situations, and applications such as this are very much an AP level skill that transcends just the basic understanding of the fundamental theorem and really requires us to link together multiple complicated ideas in one problem. I wanted to make that disclaimer because these problems are not meant to be easy. I'm purposely recording some videos to walk you through these steps, but I want you to go into every question on this page knowing that these aren't supposed to be easy and challenging yourself accordingly. If you feel as though you want to be very prepared for the AP test, or better yet, very prepared for more college level calculus, then I would hope that you can take it upon yourself to try as many of these questions without relying on the videos to walk you through. Really try to challenge yourself to at least attempt the question, or if nothing else, to look at the answer key and work backwards to see if you can figure out how the answer makes sense. These videos are meant to be a last resort in some ways because I want you to really use this as a last ditch effort to understand the question after having tried it yourself. The challenging part about AP and about college level calculus is that oftentimes you're expected to figure out these applications on your own. So while I understand that that is a lot to ask, and I know that while learning from home that's an even bigger challenge, I hope that you'll embrace the challenge if you're up for it. If that just sounds like one additional hurdle that you are not prepared for, and if any sort of thinking right now is really difficult, let alone extended applied thinking of calculus, then follow along with the videos and do what you need to do. But try, if you have the ability, to challenge yourself to maybe skip through some of the videos or maybe skip some videos altogether so that you can maintain a little bit of independence in your thinking. The first video that I want to make sure that we talk about in this playlist, or the first problem, is question number 8. Question number 8 is a derivative question. And in case you're wondering how I know that right off the bat, it's because I recognize two key words that trigger my memory of derivatives instantly: increasing and decreasing. Those are derivative words. We know that. We've seen those words so many times in the first semester that we immediately associate those words with derivative problems. When g is increasing, that means we have a positive derivative. G prime is positive. When g is decreasing, that means values of g prime are negative. So increasing and decreasing is familiar derivative vocabulary for us, and that relates us back to the derivative, g prime positive or g prime negative, and that means that we have to understand what's going on with g prime. Now, increasing and decreasing problems also often represent line chart opportunities. So line charts are going to be useful anytime you see those key words like increasing and decreasing. I'll just remind you here with this little graphic that line charts should be used anytime you see the word increasing and anytime you see the word decreasing. We'll see other situations on this page that will trigger our memory of line charts, which is why I'm making this little note at the top that we can hopefully apply in multiple examples. So let's think about what we know as we start the problem. We know that when g is increasing, its derivative is positive. When g is decreasing, its derivative is negative. So let's go with that baseline assumption. We need to figure out where g prime is positive and where g prime is negative. So that means I need to know g prime. G prime is the most important part of this entire problem. Now g is defined as a function, and interestingly, g is an integral function. But I need to analyze g prime. I don't want to analyze the integral. I want to analyze the derivative of this thing. So I'm going to have to take the derivative of both sides. You recognize that notation from the previous playlist? I need to take the derivative of both sides. That's the equivalent of writing g prime of x, but I'm using this different notation just to trigger a different part of our memory that we have been looking at in this series of playlists this week. I need to take the derivative in order to get a prime. So I'm going to take the derivative of g, that's g prime. Then on the right-hand side, I'm going to take the derivative of the integral, and I'm going to remember that the derivative of the integral, that's the second fundamental theorem of calculus. That's what we've been using this whole week so far. That's what's telling us, hey, we can use a shortcut. And I'll want to use a shortcut because sine t squared, that's going to be some sort of chain rule madness. I don't want to have to deal with that. So let's take the derivative of our integral. According to the second fundamental theorem of calculus, that's a three-step process. First step is to cancel the derivative and the integral symbols. Second step is to rewrite the function, but with something plugged in for my dummy variable. And then the third step is to multiply by the derivative of whatever's getting plugged in. That's my chain rule step. And if you're like, oh, Herbert, you don't need that third step. It's just an x. I know, and I'm just going through the motions to be consistent. That way, every second fundamental theorem problem has the exact same routine. So I did the canceling, derivative, integral, cancel. Now I need to plug in x for my dummy variable. So now I have x squared times the derivative of what I just plugged in. So the derivative of x is 1. If I clean this up, now I have sine of, in the parentheses, x squared times 1 doesn't really do anything, so there's my derivative. G prime of x equals that. So I've done the part that I needed to establish the g prime function. This is the function that I need to analyze. I now need to make sure that I make a line chart so that I can see where this g prime function is positive and negative. That's going to tell me where the function was increasing and decreasing. So in my scratch space, I'll just kind of move my scratch space over a little bit. I'll make a line chart for g prime. Now we haven't done line charts in a while, so this might be a good opportunity to just remind ourselves about how line charts work. For a line chart, I need to first establish zeros, then I need to establish pluses and minuses. Since they're telling me a limited interval to analyze, I'm going to put the boundaries of -1 and 3 into my line chart so that way I can see everything there. Now, let's think about the zeros of this function. There's nothing wrong with using a calculator, since in theory your entire AP test can now be done with a calculator. This would be a perfectly appropriate time if you wanted to graph sine of x squared in a calculator and to use the calc 0 function to establish whatever possible zeros your line chart may require. I'm just changing a few things on my graph so I can see a clear picture. It looks like I can expect 1, 2, 3 zeros here, here, and here. So if you wanted to, and if you have access to such a tool, you can do this by solving for the zeros. You're essentially, by the way, solving sine of x squared equals 0 as an equation. And I'll show you how to solve that equation by hand should you not have a calculator to use. You could also graph it in Desmos. Desmos is super user-friendly because if you just click on where a 0 looks like it's located, it'll tell you the exact coordinates. We don't have that luxury on a graphing calculator, but if you use the second calc option and go down to option 2, the 0 function, you can do the left bound, which I can just type in. You can do a right bound, and you can kind of guess where it's close, and it will give you, it will give you an actual value. Let me do one that looks a little bit nicer. I'll go here, 1, and then I'll just use 2.5, and guess. It's going to get me close. There we go. So you can get a calc 0 to work. 1.772 is one of the zeros, and you can repeat this process for the other ones as well. So should you want to, that's an option. If you wanted to solve it analytically, either because you don't have a graphing calculator at home, or you don't want to type it into Desmos and you just want to be able to do this without a calculator for your own edification, think logically about where sine on a unit circle would be 0. We're limited just to this interval, so I'm only going to think about possible values of x that could, in theory, be doable. So from -1 to 3 leaves me with very few options, but here are some options that I can think of. Sine of something has to be 0. Well, think about those locations on the circle. At 0, that's a possibility. When sine of 0 is your angle, that's 0 as an answer. Sine of pi is a possible place where you get 0. Sine of 2 pi is a possible place where you can get 0. And then, of course, this repeats. You can get 3 pi and 4 pi and 5 pi and 6 pi and 7 pi and negative pi and negative 2 pi. Lots of possibilities. But the reason why I'm thinking about these 3 possibilities is because those are the 3 most traditional options that you would see on a unit circle. So let's think logically. Remember what used to be inside of this parentheses? It was an x squared. Let's think logically. There are 3 possible scenarios here. X squared could be 0. X squared could be pi, or x squared could be 2 pi. And in case you're thinking, no, Herbert, you'd be like outside the interval, 2 pi, that's way too big. Bear with me here, because x squared has to be 2 pi. The inside of that parentheses was a square. Maybe this is actually in our interval. We should check. Now, let's think of each of these 3 things as like a disparate situation, one at a time. If x squared is 0, that means x is 0. That is one possible solution to my line chart. That is one possible place where I might have a 0, a critical point. Now, I can confirm that when I graphed it, that looks about right. It does look like there was a critical point on the graph at 0, so that makes sense. Now, what about the second option? If x squared is pi, then x must be the square root of pi. Square root of pi is the square root of 3.14, which is definitely like 1 point something. That is within our interval. So it's a good thing we didn't exclude that possibility. 1 point something is definitely in our interval. So I'm going to label that on my line chart as well. That's another possible 0. And again, confirming, I already know that this graph has a 0 at 1 point something. So it does seem to align with what I already saw. What about 2 pi? If x squared is 2 pi, then that means x is the square root of 2 pi. 2 pi is about 6. Square root of 6 is about 2 point something. So yeah, it looks like this possibility is still within our interval as well. Square root of 2 pi must be another option for a 0 on my line chart. And again, I can confirm that must have been this point here. So it's a good thing I included 2 pi as one possible answer, because the square root of 2 pi does appear to be within my interval. It looks like beyond that, it cuts off. So this point looks like it's just a little shy. I don't think I'm looking for any other points. I think I found all of my possible zeros for my line chart. So now that I've created the zeros for my line chart, now I need to put in the pluses and the minuses, which is where we plug in a test point into G prime to see what kind of answer we get. Again, I think it's fine to use a calculator for this, especially if you're not as familiar with a unit circle. So just pick a test point anywhere in between. Even if it's a decimal, who cares? At this point, let's just make sure we understand what we're doing. So pick a test point between -1 and 0, say like -0.5. I would plug that test point into G prime, because remember I'm testing G prime, so I need to look for signs in G prime's equation. The G prime equation was sine of x squared, so I have sine of, and then -0.5 is my test point, squared. I get a decimal, but I don't care. It's a positive number, so I know that that section of my line chart has plus signs. Then I'm going to repeat that process for all of these in-between areas. A test point between 0 and root pi. Root pi is like 1.7, so I'll just pick an easy little test point. Let's just pick 1. That would be sine of 1 squared. That gives me a positive answer. Then I'll pick another test point in this area. Square root of 2 pi, if I recall correctly, is like 2 point something. So to play it safe, I'll bet I can pick a test point of 2. So sine of 2 squared. -0.75, so negatives in my line chart there. And then I'll pick one more test point in between square root 2 pi and 3. If you're not sure, pick something really close to 3. That way you can play it safe, like 2.99. So sine of 2.99 squared. and I get a positive answer. Now, in case you know of another way to do this line chart, you have another option. Remember, we actually graphed sine x squared when we originally did the calc 0 thing. If you have access to the graph, you can tell the graph is positive, so values of g prime are positive. Then they hit 0, then values of g prime are positive again. Then they hit this critical point at square root pi. Then they go negative till you hit square root 2 pi. Then they go positive again. So in theory, you could analyze a graph for the line chart if that makes it easier, or you can do it this more algebraic, analytical way, whatever works for you. Nevertheless, here we finally have enough information. So remember how we wanted to talk about the intervals at which g is increasing and decreasing? Now we can tell. Now we can finally tie it together. G is going to be increasing wherever g prime is positive. So if I look at my line chart, here's g prime on my line chart. It is positive in this section, again in this section, and in this section. So it appears that there are 3 intervals in which g is increasing. G is increasing on all 3 of those pink highlighted intervals from -1 to 0, in union with 0 to pi, or square root pi, and from 2 pi, or root 2 pi, to 3. So there are 3 intervals on which g is increasing. By default then, that means g is decreasing wherever g prime is negative. So the only possible situation where that happened on my line chart is that section between root pi and root 2 pi. So that means g is decreasing in only that interval from root pi to root 2 pi. So the nice thing is it's definitely similar to line chart questions we've done before. That process of finding line chart values, finding zeros, plugging in test points, doing pluses and minuses, all of that hasn't changed since first semester. The only thing that was different was the fact that we had to do a derivative of an integral to get there. And that was where the second fundamental theorem came into place. What's interesting is that part in comparison almost seems easier than what we did with the line chart. So weirdly enough, while the new material is certainly abstract and out there, this idea of the fundamental theorem of calculus is definitely a little bit hefty. It pales in comparison to the amount of work we have to do in other areas. So the second fundamental I certainly appreciate because it didn't involve much work. Line charts would involve way more work. And that certainly makes me appreciate the fact that these abstract little shortcuts really do save me valuable time and energy. In any case, I'll just give you a heads up. Question number 9 is very similar. I purposely did 8 so that you could try 9. Because notice, question number 9 has another trigger word that means derivative, the word maximum. So just as a reminder, the word maximum is interpreted much the same as we interpret the words increasing and decreasing. Increasing and decreasing are additional synonyms for saying g prime is positive, g prime is negative. Maximum is associated with the same idea. So to figure out whether it has a maximum, we are again going to have to use a line chart. The question could have just as easily said minimum, for which we would also use a line chart. So I'm just at the top here kind of making this little graphic organizer to remind us of all of the trigger words that remind us to use a line chart. Increasing, decreasing, those are line chart words. Maximum, minimum, those are line chart words. Question number 8 didn't ask us about max or min, but we definitely could use that vocabulary. If they had asked us, we'd be well equipped to answer that question. It looks like our graph is going up, then flat, then up. So I'll make a little sketch. Up, positive, flat, up, increasing, flat, decreasing because the negative, flat, and increasing again. That must be the general shape of my graph. And now if I think about it logically, I could think, well, in terms of max or min, I don't really know where these endpoints are, but I can certainly infer that we have a local max at root pi, because the graph definitely peaked there and turned around to go back down. And we definitely have a local min right here at root 2 pi, because the graph definitely was going down and then turned around and came up. So even if I had to, I could answer a question, possibly, like question number 9, with very much the same approach. I would say that this number 8 has a local max at square root pi and a local min at square root 2 pi. Now, if it says absolute max or min, then you still have to test the endpoints, which this question, again, didn't ask me to do, so I'm not going to go down that rabbit hole. That just sounds like a lot of work. But it does beg the question, can we do anything that we used to do with derivatives in these problems? And the answer is yes. These are basically segues to force you to review a lot of the old topics. And this might be a great way of incorporating two things all in one. You're applying the fundamental theorem of calculus, which is super important right now, and you're reviewing all these line chart things, which I think is super important with the AP test on the horizon, where we have a feeling they're probably going to ask us things like line charts, since that was such a big fixture of so many lessons between the beginning of the year and now. So try question number 9, for which I'm not going to record a separate video necessarily, but the answer key is provided. If you have a question and you need explanation, you can send me an email and I'll be glad to just work through whatever questions you have via email. You can pop into office hours and I can walk you through it in person, well, in person during office hours. Or if needed, you can send me an email and just say, Herbert, I really end up needing a video for number 9. Can you end up doing that for me? And I'll be glad to walk you through that too. Either way, try number 9. And if you have a chance, try number 10, which is another line chart question. I plan on doing a video for number 10, but as I said at the beginning of this one, if you can try to do some of these without relying on the video, that will be an excellent application of your fundamental theorem skills and a great opportunity to review your line chart skills.